Greetings and welcome. Last night's homework was talking about probabilities of conditional events. It was on page 863, and it included problems from both the independent-dependent events as well as the inclusive and mutually exclusive events. So it was kind of a bit of a review from the last 2 days. So it says, problem 4, the probability of rolling a sum of 7 on the first toss of 2 number cubes and the sum of 4 on the second toss. So I think I'm going to grab a screenshot for this where I know they already drew the table out for me. Might as well save myself some time. Page 861 here apparently. Ba-bam. Ba-bam. Here we go. So, well, first of all, it cannot be both. Well, let's see. Oh wait, two number cubes being rolled. Those events are going to be independent of one another. Whatever outcome I get on the first die is unrelated to the second die. Or the second roll. I guess I'm rolling 4 dice, technically. So let's see. Rolling a sum of 7 on the first toss. Sum of 7, I believe that's this diagonal. Something like that. Those are all sum of 7. So that is, let's see, probability sum of 7, then sum of 4. So that's going to be equal to probability sum of 7 times the sum of 4 because they're independent. So this is 6 out of 36 multiplied by, well, let's see, figure out what the sum of 4 is. That diagonal is the sum of 4, right? So 3 out of 36. And I think I can cross-cancel some stuff here. 6 and 36 reduced to be 6. This 3 and that 6 becomes 2. So is that going to be 1 over 36 times 2? Is that 72? I get that problem right? Yeah. So that's the idea for that one. Also, I just want to point out that if this was an OR problem, if it said rolling a sum of 7 or a sum of 4, that these two events would have been mutually exclusive and I could have added their probabilities and not had to worry about overlap if it was a single toss of the dice. So, next question, 8. The probability of selecting a boy or, let's see, I'm guessing there's more to this problem. Oh no, here it says 12 girls, 5, yeah, okay, blah, blah, blah. Alright, probability of selecting a boy or a blonde-haired person. The probability boy or blonde. Alright. From 12 girls, 5 of whom have blonde hair, and 15 boys, 6 of whom have blonde hair. So the question is, does there ever exist a person who is both of those things? Yes, there are boys who are blonde. So this is going to equal the probability of boy plus the probability blonde. And I have to subtract the overlap, the probability of both occurring. Right? So let's calculate some of these. Probability of boy. Let's see. How many people are we selecting? It sounds like just 1 based on it. Yeah, right? Yeah. So let's see, we have 15 boys, so that'd be either combo 15-1 if you wanted to use combos, or we could just say that's, well, 15 out of, how many people total? 15, yeah, 27. Both of those are reducible, but I anticipate having to add and subtract, so a common denominator might be helpful, so I'll leave that as an irreduced fraction. Probability of blonde, 5 plus 6, yep, so that's going to be 11 out of the 27. And probability of both, there are 6 boys with blonde hair, 6 out of 27. So the overall probability is going to be 15 27ths plus 11 27ths minus 6 27ths. So yeah, that's 20 27ths. And I don't...
Where did the 6 come from?
The probability of both blonde and boy. Because if I just added these two, I actually counted the blonde boys twice. Because I added them here, and I added them here. So I had to subtract one of those addings of the blonde boys.
Okay.
So it's the overlap.
Alright.
Can it? No. Yeah, 4, 5. No. So, so there's our example of a inclusive event. If these were mutually exclusive, then I wouldn't have to subtract the scrap. That's really the primary difference between those two. Let's see. In a bingo game. Oh, wow. I forgot about this problem. We have to actually count stuff. Balls are numbered 1 through 75, placed in a bin. Balls are randomly drawn and not replaced. Okay. Find each probability for the first 5 balls drawn. So let's see. Not replaced, these events are going to be dependent on one another. And I don't believe these are necessarily or questions. This is just selecting 5 in a row that happen to have those qualities. So this is a question of independent, dependent, or these are and situations, right? Like drawing an even and another even and another even, right, is the idea. So for problem 10, first of all, we got to figure out how many evens are there. Ooh, man. Well, if I do 75 divided by 2, I get 37.5, right? Now, I know that it starts with an odd and ends with an odd. So the even must have been the 37, and the odd must have been the 38. Right? So that together they average out to being 37.5 is half of the numbers, right? So we may actually have to list out most of these in a moment to figure this out proper. Hopefully not. But let's see. So what is the probability of selecting 5 even numbers? Well, I can set up a combo. So of those 37, I want to pick 5. And what's nice about combos is they by default have dependent situations built within them. The not replacement is what it's considering. Over how many are there total? 75. And we're choosing 5. So 37 combo 5 is 4, 3, 5, 8, 9, 7. 75 combo 5 is 1, 7, 2, 5, 9, 3, 9, 0. That's 17 million. So the question is, if you're at an old folks home for the last 15 years of your life and play bingo every day, how long does it take for you to go through all 17 million combinations of that? That'd be interesting. Yeah, and how quickly they choose numbers. Let's see. Yeah, this might actually not reduce, and then they wrote it as the fraction 0.2526 or whatever is. The decimal version of that. Yeah, the calculator's frac thing's not finding a way to reduce that, but that's fine. Let's see. Actually, instead of doing 11, let me. My answer's wrong. Wait a minute. Oh, I did. There is an O in front of this. Sorry. Good call. Good call. Just to verify, I'm not just making stuff up. There it is on the calculator. Right there. There we go. I'm not just fudging this yeah, 0.025, sure. Actually, I just realized here's some OR problems. Maybe I should do one of 12 or 13. Or, let's see, which one would you like? 12 or 13, which one are you a fan of?
Well, yeah.
Actually, well, let's analyze 12. 12, 5 odd numbers or 5 multiples of 4. Question, are those inclusive or exclusive? Exclusive because a multiple of 4 is always even, so there's never going to be an odd number in that batch. So I would just find both of those probabilities independently and add them together. 13, if I look at that, probability of 5 even numbers and 5 numbers less than 30. Is there overlap there? Yeah, so those are inclusive. Would you like me to do 13? Because I think 13 is cooler. I like 13. I'm not trying to twist your arm or nothing, but I think 13 is cooler. It's cool. Here we go. Let's see. So, even numbers. Let's see. Well, P of 5 E or 5 less than 30. Hey, less than 3. We love you, Eeyore. Is going to be the same as probability 5 even plus the probability of 5 less than 30 minus the probability of both, because there is overlap. There are even numbers less than 30, like 2, for instance. So let's find the probability of 5 even. Well, we already know how many. Actually, we already know that, don't we? We just Isn't that exactly what we just calculated? Yeah, bam. So I'll just call that 0.02526. Sounds good to me. We just calculated that. Probability of 5 less than 30. So, question, how many numbers are less than 30? 29, 1 to 29, right? And I want 5 of them over combo 75, 5. So 29 math combo 5 is 118755 over the same denominator from earlier, 17 million. I really hope I don't have to play bingo when I'm in an old folks home. Like, I'm just going to connect to like the new Xbox Live then and play with all my friends from high school that I hadn't talked to in like 60 years. And I'll just be like, hey guys, what's up? Want to play the new Call of Duty? Let's see, is that a 4 or a 9? It looks like 9s. 9390. I got 0.00688. Let's see, hopefully I did that right. 117259390. Yeah, alright. And now we've got to find the probability of both. So we've got to figure out how many even numbers are less than 30. Now the number of numbers less than 30 was 29. So how many of those are even? Well, we could do 29 divided by 2. And that's going to be what, 14 and a half? So the even ones must be 14, the odd ones must be 15, because that adds to 29. Since that list starts with 1 and ends with 29, both of those being odd, there had to be more odd numbers in the list than even. So this is going to be combo 14.5 over combo 75.5. So this is the overlap that we're going to have to subtract. That's an ugly 5. Well, it takes a little while to get used to it. 2002 over 17 mil 259390 equals 17259390. Let's see, that's going to be 0.123. Yep. 116. So it's not that much. Not that likely of getting all evens less than 30, but that's what it would have been. So my overall probability would have been the 0.02526 plus 0.00688 and minus 0.000116. So let's plug that in. 0.02526 plus 0.00688, and I'm gonna get, hopefully this is right, 0.032024. Yeah, nailed it. Bam. How about that? So yeah, so this was kind of cool. I like the idea of having to figure out how many even numbers were there. Good stuff. Good stuff. All right, we're at 16 minutes. I'm going to keep doing 15. We'll do it. 15. Sports. Last problem. Deportes. Let's see. A baseball team's pitching staff has 5 left-handed and 8 right-handed pitchers. If 2 pitchers are randomly chosen to warm up, what is the probability that at least one of them is right-handed? Let's see. 2 pitchers are chosen. So the probability of at least 2 right-handed. What's another way I could phrase that? Actually, at least one of them is right-handed. Sorry. That's why. I was like, wait a minute, that's not a very good at least problem. So yeah, that's the same as the probability of one right-handed or one left-handed. I guess I could phrase it this way. Sorry, or 2 right. Man, why am I not just saying the words that make sense? And this or problem, well, technically one right-handed is that situation. So the question is, do those outcomes include overlap? Well, this is exactly one right-handed and exactly 2 right-handed. So there is no overlap. If I wasn't specific, then there would have been. So these are actually exclusive. So that means I can just add their probabilities. So probability of one right-handed. How many right-handers? We've got 8, so that's combo 8-1. But where am I picking my second pitcher from? The left-handers. So I'm going to have to consider the outcomes of who that other one was picked from. If I only had this as my numerator, I'm not counting all of the possibilities. And I don't want to leave it to chance of just picking the other guy from either left or right-handed because I wanted specifically exactly one right-handed. So I have to ensure that the second guy is a left-hander. All right. Over combo, there's 13 people on the team? So 13-2. So that's that setup. Probability of 2 right-handed is going to be combo 8-2 over combo 13-2. So this is 8 times 5 is 40 over combo 13-2. I think we've done that one before. 78. I'm not going to reduce that. 8 combo 2. Is that going to be 28? Nope, I wouldn't have guessed that one. 78. And since there's no overlap, I can simply add those fractions. 40 78ths plus 28 78ths is going to be 68 78ths. And that reduces to 34 39ths. Okay, yeah, it only reduced once by 2. And was that right? Bam, got it. No, we're good. We're good. This will probably be on a test at some point. So thanks for watching, Internet friends. Have a great day.